All right, in this lesson, we're going to be covering structural isomers and what exactly they are, and then we're going to move on to naming and drawing alkenes as well as alkynes. So for structural isomers, essentially what they are compounds that have the same molecular formula but a different structure and therefore different names. So in other words, you have the same molecular formula, but the atoms are arranged differently. So, atoms are arranged differently. It's another way to say it. Okay, and because the atoms are arranged differently, that's going to give rise to different properties for different isomers there. So the arrangement of the atoms determines the types of intermolecular attractions, which then determines properties such as boiling point as well as solubility in water. So, for examples, we're asked to draw and name the 3 structural isomers for C5H12. All right, so easiest thing that we can draw, and I'm just going to go for line diagrams here. Okay, so 1, 2, 3, 4, 5. So that's 5 carbons there. So I'll make them super clear where they are by highlighting them with these blue dots. Okay, now for line diagrams, the hydrogens are implied. So let's count how many implied hydrogens there are here. So there's 1, 2, 3 implied hydrogens for this carbon. How I know that there's 3 is because each carbon atom needs 4 bonds. It already has 1 bond here, so it's going to have 3 hydrogens to make up the remaining 3 bonds that that carbon atom needs. Okay, for this carbon, it already has 2 bonds, so it has 2 implied hydrogens. Same with this one, and then this last one has 3. So if we count all of that up, 3, 5, 7, 9, 12. So this is 5 carbons, 12 hydrogens, which is what we were aiming for here. All right, for this next one here, we can go 1, 2, 3, 4, and we can have a branch right here. Okay, so let's just count up our carbons. 1, 2, 3, 4, 5. Now let's count up our implied hydrogens just to make sure we're doing this right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now keep in mind for this diagram, if you really wanted to, you could have drawn it something like that. Here, I'll make this a little bit longer here. And we still have 1, 2, 3, 4, 5 carbons, and we still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. Okay, so this and this, they are the same compound, but they just look a little bit different. Okay, and if you wanted to try your hand out at, okay, what would be the name of this? Both of these, right, for naming them, remember we need to figure out, okay, our parent chain. So their parent chain would be here and here. So keep in mind these parent chains are in the same location. Even though both of these compounds look different, they're still the exact same thing. Okay, so notice how these branches, if you give the lowest number, right, to your carbons in your parent chain, both of these are on carbon 2. How you figure that out? So you count 1, 2, 3, 4 for this one, and then 1, 2, 3, 4 for this other version of the same compound. So if I was to name this, it would be 2-methyl butane. Okay, so for both of these, that is the name. Okay, so 2 just means our branch is on carbon 2 for both of these versions of the same compound. Methyl just means for both of them, the branch has 1 carbon in it. And then butane, but means that the parent chain has 4 carbons in it. Ane just means that there's only single carbon-carbon bonds. Okay, so even though these two drawings look different, they are the exact same compound. Okay. For the third version of it, or the third isomer, I should say, you could go 1, 2, 3, and then 1, 2. So here's where the carbons are. 1, 2, 3, 4, 5. For our implied hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So with figuring out isomers, the best way to figure out what possible isomers are is just to play around with the placement of the branch or how many branches you have in your compound. Okay, and if you're trying to figure out, and you maybe have 2 different drawings and you're not sure if they're 2 different isomers or 2 drawings that look different but they're actually the same compound, try naming the compound to see if that helps you figure out whether your 2 drawings are different or the same. Kind of like with how we did for isomer number 2. Okay, so this is a practice question. Give it a shot. But I need to move on to how to name and draw alkenes. Okay, so alkenes, these are unsaturated aliphatic compounds. So what does that mean? So alkenes, they are basically carbon chains that have double carbon-to-carbon bonds. So because we don't have the maximum amount of hydrogens attached to our carbons, because of the presence of double bonds, that's why it's unsaturated. And we call these aliphatic because there is no benzene ring in these compounds. As a reminder, a benzene ring looks like this. Okay, so there's none of these in these compounds because if there was any benzene rings, it would not be qualified as aliphatic, it would be qualified as aromatic. Okay, so the general formula, so one way that you can tell if something is alkene is it'll have a formula like this. So remember, N is just a placeholder for a number, so you'll have a certain amount of carbons, and the hydrogens will be twice the amount of carbons that you have. Okay, so key feature of alkenes is they have at least 1 double carbon-to-carbon bonds. Okay, and they're gonna be unsaturated, and the reason why they are qualified as unsaturated is because you don't have the maximum amount of hydrogens attached to each carbon. okay, because of that double bond. Okay, now since there's a double bond in an alkene molecule, that means there's a new type of isomer. So the double bond can exist in different places in different molecules. So some examples of some alkenes: C5H10, C20H40, C100H200, so on and so forth. Properties of alkenes: they're going to be nonpolar, no hydrogen bonds, and therefore they're not soluble in water. So just as a reminder for hydrogen bonds, you have a compound that can hydrogen bond if you have hydrogen directly attached to either oxygen, nitrogen, or fluorine in your compound. Okay? If you don't have that, then there's no hydrogen bonding. Okay. Now, alkenes, because of the presence of that double bonds, they're more reactive than alkanes, and that double bond's just a little less stable than the single bonds. So where you're going to find alkenes is in plastic. So with PVC, that's just polyvinyl chloride. So you might have seen that as PVC pipes. Okay, it's a type of plastic. Rubber, ethylene, which is used to make ethylene glycol, which you would know as antifreeze. Some naming rules for alkenes: for continuous chains, so that means you don't have any branches, you need a prefix to denote the number of carbons, and then the last part of your name for your alkene is going to be ene. So the prefix is that meth, eth, prop, bute, pent, so on and so forth. Okay, before we called it a stem name, but prefix could also be used. It's a little bit interchangeable there. So that's important. Now, the number of carbons to give the double bond, you're going to always want to use the lowest number, okay, and state that number that the double bond is on before that ene part, okay? The number where the double bonds, that should say, start is to be given as you have a dash, number, and then dash. The reason being is because dashes separate letters and numbers. Okay, so for example here, we're going to look at this compound, we're going to name it. So first thing first, figure out where your parent chain is. So it's right here. We're going to number our carbons, and we're going to number our carbons so that the double bond gets the lowest number. So 1, 2, 3, 4. Okay. So in my parent chain, there's 4 carbons. The prefix or the stem name that means 4 is bute. But now, instead of saying butane, so ane, that ending is only for alkane, so only if you have single carbon-carbon bonds throughout your entire compound. But because of the presence of this double bond, we can no longer use that ane ending. We have to switch to ene, okay? And I want to specify that it starts on carbon 1, because that's the lowest numbered carbon that it starts on. So we can name it butanene, or alternatively, so this is only for double bonds or triple bonds that start on the first carbon. You could also name it butene. The absence of a number means that you can assume it starts on the first carbon. Okay, so both of these are right. So Just know that for double and triple bonds, if it's on the first carbon, you don't have to specify the number of carbon it starts on. However, for branches, you do need to specify forever and always the carbon number that it starts on. A branch is never going to start on the first carbon, because if it is, that means you're mistaking a branch, or you're mistaking a part of your parent chain for being a branch. That would be the problem if you ever try to say that you have a branch on carbon 1. Nope, your parent chain is part of that branch, okay, or part of what you're thinking of as a branch in that scenario. So always denote the carbon number for branches. So always denote the carbon number for branches, but with double and triple bonds, if it's on the first carbon, you don't necessarily have to write it, but if it's on anything higher, any double bond or triple bond is on any carbon number higher than 1, you absolutely must say it. All right, for branch chains, find your parent chain that contains the double bond. So double bond must be in your parent chain, and number it so that the double bond gets the lowest number. Okay, so you're going to give the double bond higher priority over branches when you're numbering your carbons. That's very important. So to name, you're going to name the groups first in alphabetical order, and you're going to include the number of carbon where each is found. Then you're going to have the number for the double bond, and then name for the longest chain. Okay, so those are all pieces of the puzzles that you need to be including here. All right, so let's look at this first one. We need to figure out where our parent chain is. So could we go like this? No, because that does not include your double bond as part of your parent chain. That's why you can't do that. So instead, the longest continuous chain that includes the double bond is going to be right here. Now I'm going to number my carbons and make sure that the double bond gets the priority for lowest number. So 1, 2, 3, 4, 5, 6, 7. All right. There is my branch, and that's all I want to do before I start naming this. Okay, so remember, branch names comes first, then parent chain. So talking about my branch first, looks like my branch is on carbon 2, and it has 2 carbons in it. So the stem name that means 2 carbons is F, and it's on carbon 2. So 2F. If I want to talk about a branch, I need to end its name in YL. Okay, so that's the branch. Now I need to talk about the parent chain. So the parent chain has 7 carbons in it. So that stem name is hept. Okay. And I have a double bond on carbon 1. So I could go hept 1-ene. Or alternatively, what I could do is I could say 2-ethyl heptene. Both are acceptable. The reason being is because the double bond is on carbon 1, or it starts on carbon 1. All right, let's go to the next one here. So it's tempting to go, this is my parent chain. However, that's not the longest continuous chain of carbons. Okay, so this option had 1, 2, 3, 4, 5, 6, 7 carbons in it. However, if we go like this, then this is going to have 9 in it. Okay, so I'm going to number my carbons, making sure double bond gets the lowest or the priority for the lowest number. So that's why I'm starting left and going right. Here are my branches. Keep in mind, I'm just circling the branches to make it easier to see for myself. All right. So, branches, we got to talk about that first. There are branches on carbons 4, 5, and 6. All of them have 1 carbon in it. So, all of them are methyl branches, but since there's 3 of them in total, on carbons 4, 5, and 6, I need to say tri to mean there's 3 in total. So trimethyl, so that's the branches taken care of. Now I need to worry about my parent chain. So there's 9 carbons, so that's non. And my double bond starts on carbon 2, so non-2-ene. So I absolutely have to put that 2 there because I need, like, otherwise if I don't, people will assume that you mean that your double bond starts on carbon 1. So that's why it's absolutely important that you write that 2 there. So let's just write that as a note. Okay, moving on to the next one, we got a line diagram. So looks like the parent chain is going to be here. Again, remember you must include the double bond as part of your parent chain. Okay, so how I'm going to number these carbons to make sure the double bond gets the lower number. 1, 2, 3, 4, 5. Okay, the other option would be 1, 2, 3, 4, 5. So notice how for the purple numbering, the double bond starts on carbon 2, but for the pink numbering, double bond starts on carbon 3. You always want to use the lower number. So that's why I'm going with the purple numbering here. Okay, and we got a branch right there. All right, so it looks like the branch is on carbon 3. It has 1 carbon in it, so 3 meth, and then YL to mean that it's a branch. Okay, now we're talking about the parent chain. So it has 5 carbons in it, so pent 2, because that's what carbon the double bond starts at. Ene, so ene specifically means there's a double bond there. All right, moving on to alkynes. So alkynes are just meaning that you have an organic compound that has at least 1 triple bond in it. It's a main feature of it. Okay, these compounds are considered unsaturated because of that triple bond. It prevents some of your carbons from having the maximum amount of hydrogens attached to them. It's aliphatic because the compounds that we're going to be talking about in this section does not have a benzene ring in it, so it is aliphatic. The general formula for alkynes is going to be you have a certain amount of carbons and your amount of hydrogens will be 2 times the amount of carbons you have, subtract 2. Okay, so now that we're talking about compounds that have triple bonds in it, we got a new type of isomer. So that just comes from, you can change where your triple bond is to create different molecules. Okay, now in nature there's not very many alkynes, and that's just because alkynes are not a very stable compound there. Okay, so some examples would be C5H8, C20H38, C100, 198, so on and so forth. All of them follow that general formula up here. Okay, so for properties, they're very reactive. Okay, they're very reactive because they are an unstable compound because of that triple bond. Okay, so what makes the triple bond unstable is because you have 6 electrons all in the same area, so there's lots of repulsion happening there. They're nonpolar, they have no hydrogen bonds. So as a reminder, hydrogen bonds only exist in compounds where you have hydrogen directly attached to oxygen, nitrogen, or fluorine. Okay, and because they do not hydrogen bond, they are not soluble in water. So boiling points are going to be higher than corresponding alkanes and alkenes because of their linear structure and nature of triple bonds. So if you're comparing the boiling point of alkanes, alkenes, and alkynes, and let's say all of these compounds, the alkane, the alkene, the alkyne, they all, let's say, have 3 carbons in their parent chain. The alkyne will have the highest boiling point, the alkenes will have the middle boiling point, and the alkanes will have the lowest boiling point, even though all of them have 3 carbons in them. Okay, uses, you can see triple bonds in acetylene, which is also called ethene, and you use that for welding torches. And for naming rules, so continuous chains, those are the ones that don't have any branches to it. You're going to have the prefix to denote the number of carbons, so meth, eth, prop, bute, pent, so on and so forth. And you're going to make sure that you end your name in YNE. YNE specifically means you have a triple bond. So same purpose as the ENE ending in alkenes, meaning that there is a double bond somewhere in your compound. Okay, so maybe let's actually go back and just write that in. Specifies there is a double bond in compound. There we go. Okay, so rules are very similar to alkenes as well as alkanes. It's just we got this YNE ending, and we do need to specify what carbon the triple bond starts at. Okay, you're going to give preference to the triple bond and make sure that it's getting that lowest number. And the number where the triple bond starts is going to be given as dash number dash between the prefix. So the prefix that tells you how many carbons are in your parent chain and the suffix of YNE. So if we look at this, here's my parent chain. So I'm going to number this from left to right because that's what's going to give my triple bond the lowest possible number. Okay, so there's 5 carbons in this parent chain. So that means I'm going to say pent. And then I want to specify that the triple bond starts at carbon 2. So I'm going to go -2 YNE. Done. Okay. For branch chains for alkynes, you need to find the longest carbon chain, longest continuous carbon chain, or in other words, your parent chain, and number it so that the triple bond gets the lowest number. So to name, you're going to name your groups first in alphabetical order, including the number of the carbon where each is found. Then you're going to number the triple bond, then name the longest chain. Okay, so those are all pieces that you need to include or be aware of when you're naming alkynes. So let's look at this example here. All right, so parent chain. Very tempting to go, that is my parent chain. However, how many carbons do we have? 1, 2, 3, 4, 5, 6, 7. Okay, but what if we went like this? That would have 1, 2, 3, 4, 5, 6, 7, 8 carbons in it. So that is the longest continuous chain. Okay, if you're thinking to yourself, wait a second, couldn't I just go like this? Because there's 8 carbons there. Absolutely, you could. You will get the same answer for your name. Okay, but I just like going like this just because it's a little bit easier in my brain. Okay, and you get the same result in the end. So here are my branches. Okay, I'm going to give preference here to my triple bond. So let's go 1, 2, 3, 4, 5, 6, 7, 8. The reason why I'm not numbering it the other way, because for the purple numbering, my triple bond starts at carbon 3. If I did the pink numbering, my triple bond would start at carbon 5. That's why I need to go with the purple numbering. Okay, so branches, we need to talk about those first. Looks like there's 3 methyl groups, and they're on carbons 2, 5, and 6. 3 in total, so tri. Meth, because there's only 1 carbon in each. YL, because they're all branches. YL suffix means that you're talking about a branch. Okay, so that's the branches taken care of. Let's look at parent chain. So there's 8 carbons. So the stem or the prefix, whatever you want to call it, to mean 8 is oct. And then we got to talk about our triple bond. So oct 3-ine. So 2,5,6 trimethyl oct3-ine. Okay, the rest is practice, so there we have it.